Hi everyone, this video is for section 6.8, problem solving using rational expressions. So basically we're going to be taking a look at word problems. In this particular case, we have a kayaker can travel 1.2 miles downstream in the same time it takes him to go 4/10 miles upstream. If the river current flows at 2 miles per hour, what is the kayaker's speed in still water? So I understand that reading this problem initially probably seems overwhelming. You're probably getting a lot of images kind of flashing through your head and you're not quite sure necessarily how to start. So what I would suggest doing is boiling this narrative down into kind of a table of information that might help you focus a little bit more. So before we do that, I again recommend you to pause the video and read through this problem a second time just to see what information is being provided for you. Okay, so let's begin. I'm going to go ahead and create a table. And from this table, I will go ahead and populate some information. So I do note that this problem is talking about two cases. One of these cases is going upstream, and the second case is going downstream. So let's go ahead and just jot these two cases in. Notice that they're also talking about, they're giving you things such as distance. So they're telling you, oh, I've traveled 1.2 miles, for example. And they're also giving you time. Okay? They're also giving you a rate. So in this case, what I'm trying to get at here is that they are discussing a very familiar formula that we've probably seen, and that formula is distance is equal to rate times time. Okay, so from here, let's go ahead and dig a little bit deeper, or let's go ahead and populate this information. So with regards to downstream, I know that a kayaker is going to travel a distance of 1.2 miles downstream. In the same time, it takes him to go 4/10 of a mile upstream. So I have this information populated in. Okay, and let's just kind of take a moment and kind of see if that makes sense. So if I'm going downstream, that means that the current is going with me. So it's pushing the kayak along the way. So I'm getting help. Not only am I paddling my way down this stream, but the current is also pushing with me. So I get to go a little bit faster. I get a little nice oomph or whatever. With regards to upstream, then I'm fighting the current. So I'm traveling against it. So I have a lot more friction that's happening between the boat and the current. So that would explain why I'm not able to cover as much distance in the same amount of time when I'm going upstream versus when I'm going downstream. But let's see what else I have here. I do have a mention of this notion of the same time, but they don't give you a time. Notice that they haven't said like, oh, you're going to be able to do this in 30 minutes. So I know that my time is the same, so I'm going to use the same variable, okay, just t, all because in this problem they're not giving me any other information. With regards to the rate, we can be a little bit sneaky as well. So with regards to the rate, we know that the river's current is 2 miles per hour, but I don't know how fast I'm going up the stream alone. So assuming like if the current stopped. So if I was in still water, I don't know how fast I'm paddling upstream or downstream. So I know that in this case, I'm going to, when I'm going downstream, I'm going to have my rate and I'm going to add 2 to it to represent that 2 miles per hour that the current is giving me. So here I'm using plus because I know that the current is going with me and it's helping me, it's pushing me along. When I go upstream, I have the opposite happening. You're going to have my paddling rate, and then I have to remove 2 miles per hour because I'm fighting against that current. Okay, so what I'm going to go ahead and do now is I'm going to kind of make a note here. I do have notice that if I take a look at 1.2 is equal to x plus 2 times t, I'm going to get t alone here. So I'm going to divide both sides by an x plus 2. I'm also going to take a look at my downstream. And again, I'm going to divide both sides by an x minus 2 to get t by itself. So I want you to kind of notice what is happening here. I'll leave that table up so we can see it. So I have 1.2 is equal to x plus, or sorry, 1.2 all over x plus 2 is equal to t. But I also know that 4/10 divided by x minus 2 is also going to equal t. So what I'm kind of trying to get at here is, if you recall the transitive property, so the transitive property states that if A equals B and B equals C, then A must equal C. So I found a value that kind of links these two together. So I'm basically just going to kind of skip over him and just connect these two together. Notice that T is your link in this case. So what we can do is we can link them up together. So if I know that T is equal to 1.2 all over x plus 2, and T is equal to 4/10 over x minus 2, I can argue that these two rational expressions must be equal to each other. Okay. So what I can do from here is I can do some cross multiplication, because notice that I have a proportion. So I have two fractions set equal to each other. So this is going to give me 1.2 times x minus 2 is equal to 4/10 times x plus 2. I'm going to go ahead and distribute that in. And this is going to give me 1.2x minus 2.4. And that is going to be equal to 4/10 x plus 8/10. And from here, we're going to go ahead and I'll move this up, and we're going to combine like terms. So I'll subtract 4/10 from both sides. 4/10 x, I should say, pardon me. So this is going to go ahead and give me 8/10 x minus 2.4 is equal to 8/10. We'll add 2 and 4/10 to both sides, and this will give me 8/10 x is equal to 3.2. Divide both sides by 8/10, and we get that x is equal to 4 miles per hour. Okay, so we know now, if we were to come back up to our table, the kayaker's rate of speed is going to be 4 miles per hour in still water. Okay, so that is our solution. If you have any other questions or need any additional help, please let me know.